Hello, class. Part one of the skin. Hopefully you guys got some basic anatomy, epidermis, dermis, hypodermis. I ended up talking about skin color, and relatedly hair color. And remember the pigments, eumelanin would be dark, and then pheomelanin will be the reddish yellowish color. And so what gives us our skin tone is a combination of those pigments. All right, second half. Well, your skin is where you really absorb the environment. You get, there's nerve endings throughout all of your skin, lots of them in sensitive areas, your lips and genitals and your face, your tongue, lots of nerve endings, and less like in your elbow and the back of your leg, things like that. So we'll see how we concentrate our nerve endings where we interact with the environment and where we really need those sensory inputs, right? But yeah, I'm looking at these whiskers on your cat. Even in darkness, they have sensitive hairs that come out that can tell them the size of a hole where they can get through it, things like that. Sea lions or walruses, we use these as tactile receptors deep in the dark ocean. They're looking for clams in the mud. So our hairs too, they can use to sense. Someone touches the back of your neck, you feel those hairs. The nose hairs, that's just a joke. Those are used for filtering so bugs don't get up into your nasal cavity. But yeah, what can we do? We can tell the difference between velvet and formica table, tell the difference in the texture. We can read braille, right? We can tell temperature and lots of pain receptors, right? You get that paper cut, you know exactly where that's coming from. And all of our hairs have nerve endings on it. So someone touches you, just even the hair, it sends that signal to you that, hey, someone's touching me. All right, two kinds of nerve endings we'll talk about. Special receptors for touch. One of these big ones, these lamellated, like lamella means layers. Yeah, and so it looks like an onion. It has all these layers around it. In the middle is the nerve. And so when you press on this onion, it feels the pressure, and it's going to cause this nerve to send signals that go up to your brain saying I'm being touched at a certain part of my body. You have some of these in internal places too, so you can tell the fullness of your stomach and other organs. You can feel pressure within. So these big ones, look at that, a millimeter. You can see these with bare eyes. These are huge touch receptors that are found deep in your skin and other places in your body that give you deep pressure, vibrations of deep pressure. Yeah. Look at this. That's huge. It's huge. And all the size of it, like, here's, oh. Yeah, we're looking at the size. This is adipose tissue, right? So this thing is huge. And so the nerve, the raw nerve is in the middle and has layer and layer and layer and layer around it. And so when that's pushed, it feels that deep pressure. And looking at this big picture of skin, you can see it's deep within the skin, right? It's down in the hypodermis even. So it's below the dermis. See the dermis here? And so these things you can see when someone's going to touch you big time, right? Not sensitive little feeling little tiny hairs or anything. And tactile corpuscles are the other ones. And so these are tactile touch. These are very small. They're right near the surface of the edge of the dermis and the epidermis, right near, as close as they can be to the surface. And so these things, when you look at them, look a little different. They can have a spiral look to them, but again, they have a nerve in the middle, and they are sensitive to touch, especially fine touch. And so you'll see these in places like your lips and your fingertips, especially where you have the ability to really distinguish among differences in texture, not just big pushes. So here, beautiful, look at this, look at the skin. You can tell it's got a big keratinized layer, but look at these. And these used to be called Meissner's corpuscles, and the lamellated were called Pacinian corpuscles. But now we're going to these easier terms. Like lamellated means, oh, it's like laminated. It has many layers. It has many layers on it. And tactile corpuscles are touch ones. easier. No one remembers Meissner or Pacinian. So just so you know, you see MC. Okay, that's what that means. But look, they're way up here, way up here in those dermal papilla, really close to the surface, right? Oh, look at those. I think I have even closer one. Yeah, really getting in there. Can you I can kind of see a spiral look to it, a little spiral look to it. And they're always way up by the surface and just again in sensitive places in your body for sensitive touch. Tactile corpuscles. This weird little thing, right? It's called a homunculus, they call this thing, but what the hell's going on? This is a weird looking dude here, right? Well, what this is showing is that it's the distribution of touch receptors or receptors in our skin. We'll look at this when we look at the brain too. We'll see how much of the brain is devoted to your lips and tongue and fingers as opposed to your back or something like that. So you can see what's really emphasized here is not your elbow, right? It's going to be your hands, and to a lesser extent your feet, but especially your hands. Just you have all of these touch receptors, and so much of your brain is devoted because that's how we sense the environment. We pick up something to eat, and then our lips and our tongue and our face too. Our lips and our tongue especially, tons of touch receptors. So we know the texture of the food that we're eating, or something that hits our lips. Is it safe? Is it too hot? You know, so we have all these sensors here. Cool. All right, let's talk hair. And if you think about all the billions spent on hair color, hair products, barbers, hairstylists, dry shampoo, mousse, I mean, all these things that are involved, because it's just a part of our hair and our face is what we present as our appearance. And so we spend way too much time and money worrying about it. But anyway, we are covered in hair. Humans are, it's called the naked ape. We are the hairless ape, really. But we do have hair, especially on our heads. But throughout our body, even it's very just fine hair in some parts of your body. But if you look carefully, there are tiny little fine hairs almost everywhere. They're not on your palms. They're not on the soles of your feet, your areola of your nipple. External genitalia doesn't have hair, some of it. Yeah, so lips. We don't have hair some places, but otherwise, even places that appear hairless, if you look carefully, you have little tiny hairs. And hair is a fascinating subject. You think about it. Some of us have fine hair, some of us have thick hair, right? And then color varies. And you know, babies' hair is so fine and thin. They still smell good too. Babies, you're going to see there's a certain time period when you get a teenager and they start needing deodorant, things like that. So anyway, we'll talk about exactly why that is. But look at this. You can see that people vary in how thin or thick their hair is, right? Some of you out there know that you have coarse hair and some have very fine hair. And then look what happens as you age. And again, I'm not going to ask you these numbers at all, but imagine a baby has 1,100 follicles per square centimeter. By the time you're 25, that's chopped in half. And look, by the time you're 30, it's chopped in half again. So you can see how our hair goes from being very dense as a baby. And then as we get older, it gets thinner and thinner and thinner and thinner. And these hair follicles, you wonder, your hair normally is growth, has a period of growth and not growth. And so an individual hair, I believe you can look at different stats, but I think it lives about 2 to 6 years of an individual hair. And then it stops growing for a period of months. And then it will fall out. So you're always losing hair. Every day you lose some hair and the new hair will grow behind it. And so each follicle can make many hairs in a lifetime. Until as you get to be very old, you see you have less hair. I mean, your skin changes and you have less and less hair. Yeah. And of course it grows out. So it doesn't hurt to get a haircut, right? The hairs that you see are just dead keratin, right? But inside the follicle, if you pull a hair out, you feel that because that's where the hair begins in your scalp. Yeah, what's the purpose of hair? Well, I think in most animals, you think about insulation, right? You'll see a bird has feathers, but a mouse will puff up. And even you, when you're cold, you get goosebumps. Your hairs will stand up to try to trap more air. So it's beautiful insulation, hair is. And then you wonder in humans, we leave hair on the head and then in males on the face, but in your groin and in your armpits, we adults have hair. And one idea is that we're going to see we also have these glands, these stinky glands, and that hair may, those filaments may take that chemical and like spread it out so that it's carried by the air if you're trying to advertise those scents to potential mates and such. And I know that sounds weird thinking about humans today and what we spend on deodorant and showering, trying to avoid the scent. We replace it with other scents that we think are desirable, right? But our basic primal idea is that scent was probably more important in the past, and that hair allows us to broadcast that scent, to move it over a larger surface area. So definitely a hypothesis, something you guys will think about now. Yes, and so our temperature regulation, hair can be useful for that. Protects us from, I know I have bald friends that wear a hat, protects us from UV radiation, also keeps your head, and I guess they wear a beard in the winter time. I see if the goatee works for me, but we'll see if that helps insulate us as well. Although humans, we've invented down and Gore-Tex and all kinds of things. But another thing is that humans, we're really tropical animals. We have no business living in Maine, right? In the winter, right? We're just helpless without our technology, right? So we are well suited to warmer climates with our naked skin and our inability to really do that. But we've invented air conditioning, heaters, down jackets. And so we have expanded around the globe. But if you want to think of us as a species, we are ill suited to living in Maine and Nova Scotia, right? All right. So yeah, another thing, temperature regulation, we'll talk about sweating. Yes. So back to hairs. So hairs are epidermal derivatives. They come from epidermis that dives down deep into this follicle that will go now into the dermis, even in the hypodermis sometimes. So our hair follicle goes very deep within our skin, but it originated at the surface, and it just makes this long follicle deep in there. And of course, our hair influenced by hormones. You all know puberty, you start growing hair in places you didn't have hair. And then with hormones, you also know sometimes women around childbirth will lose a bunch of hair, or sometimes birth control is recommended to fight hair loss in women too as well. So estrogens and androgens, testosterones have a big influence on our hair. They begin at developing a puberty in other places. And men having more facial hair generally than women, as is under the influence of testosterone. And with it, men are much more likely to have hair loss than women, although both can have alopecia, loss of hair. Oh, we can talk about it here. Yeah, that's my brother. My brother Steve. I got more hair. We both started out with a lot of hair, but he lost his. And so that's my dad in the background. He's got hair too. So baldness is, you guys hear all kinds of things about, oh, it's from my mother's father. It comes that way. There's genetic component to it, but there's not just one bald gene. You can see there's genes on both nuclear, autosomal, and sex-linked genes that are involved with baldness. And a lot we don't know. Some that hormonally cause, age causes baldness. It's going to happen with age. And of course, there's a lot of people spend a lot of money, Rogaine and things trying to bring back the hair and hair grafts and all these things and wigs. And so, I mean, sure, our appearance is important, and I like the bald look. I say that I have hair maybe, but to fight it sometimes, it's a big battle, and is it worth it? But I digress, right? But biologically, we have a lot of research on baldness. We know it has several different causes it can come from. Some autoimmune, where you actually attack your hair follicles, and we have the ability to move follicles too around and regain hair where you didn't have it. But anyway, baldness, it's going to affect 2/3 of men over the age of 35 will have hair thinning. And women, it's closer. I'm not sure that, I don't want to tell you stats I'm not sure of, but it's much less, but also women have hair thinning as well. And so it's just more common in men. So we can see the influence of androgens or testosterone is clearly important to hair growth. All right, so let's look at the hair itself. Look at the anatomy of the hair. And so what you have is this follicle. I mean, the hair shaft comes out, but the follicle goes deep within deeper than the dermis, and it's out on the hypodermis. And you can have at the end of it this little dermal papilla that comes up. You're going to have a hair bulb at the ends. There's a little bulge here. And you're going to have stem cells. Stem cells, just like you have in the stratum basale of your skin, that are continuously making keratin, making these cells. And the cells are going to make a hair shaft. And the hair shaft, the division is deep in your hair follicle. The hair shaft is going to be pushed out, kind of like a rocket in a silo. It's going to be pushed out this silo, this sheath, this dermal tube. The hair shaft is going to come out. It's going to grow your hair from the base. So cutting your hair doesn't influence how fast it grows. It's going to continually grow out from the base. I love this. And so each hair shaft is accompanied by a sebaceous gland. As often, if you look at a whole bunch of sebaceous glands, they're making sebum, which is oil. And remember, this is a holocrine secretion. So the cell builds up this oily, fatty substance and then explodes. And all this debris and sebum leaks out of ducts onto the hair shaft. And so it's going to help keep your skin pliable, oily, and it's going to keep your hair shaft lubricated with oil. You know, we fight it by washing it with detergents constantly, but keeps your hair from being brittle, having the sebum on it. Yeah. Sebaceous glands, they go with every hair, but they open a few places. They'll be on your areola, especially nursing. You want to keep that from being chapped, you know, and the corners of your lips have sebaceous glands. Sometimes you'll get a little like white kind of substance on there. So there'll be some sebaceous glands opening to just to the bare skin, but they're mostly associated with hair follicles, not all hair follicles. Yeah, looking at this, each hair follicle has a muscle, some smooth muscle called erector pilli. Pilli means hair, and erector means it's going to erect. It's going to cause your hairs to stand up. So you have muscle, you'll see with every hair that keeps it to, you get goosebumps. You know, if you don't have any hair, you still have little muscle that causes the skin to bulge there. What else do you guys see? You see the epidermis here diving deep into this follicle of the hair. Yeah, beautiful. That layer of the skin I didn't mention is a stratum lucidum. You see it in some thick skin. It's kind of a clear layer between the granulus and the corneum, but I won't ask you about that. And also it's going to show you here, I'll talk more about sweat glands, but sweat glands will be down here deep, and then they'll have a duct that comes out to the surface to make sweat come out. Beautiful. All right, so the keratin on our skin is a particular form, kind of scaly like that. You make keratin that also makes your hair and your fingernails and toenails. And so keratin is a protein. It's awesome, it's flexible, it's waterproof, but we can make it in various forms. We can make it more compact and filamentous, like in your hair. We can make it compact and sheet-like in your nails, or we can make it in your skin, where it's kind of fibrous and it kind of sloughs off your skin. And when you look at a hair, you guys, you know, all the hair product commercials, your cuticle. Yeah, so you have a cuticle or the squamous cells on the outside, and they kind of surround the hair, bigger hairs. And actually bigger hairs will have a cortex and medulla even like that. Very fine hairs, you may not see this kind of structure, but a normal hair is going to have a cuticle on the outside and then a cortex and medulla, kind of a little difference in the outer and inner part of the hair. And the hair comes up through this sheath. This is a cut through a hair, you know, just like this. So you can see you have the dermis is going to make this sheath around it, and the hair follicle will come up out of it and will grow out. Yeah, close up. So yeah, there's a hair, you're looking at it, yeah. The hair itself is here, and see there's some space around it. That's where sebum will dump into it, and then it's in this like tube around it made of the surrounding dermis. Beautiful. Here's a slice through hairy skin, and so you see a whole bunch of hairs. They're cut at different angles because the skin is cut at different angles. Yeah, beautiful. And you see how deep it is? We're in the hypodermis. We're way down here, but there's always a connection all the way up to the epidermis. And I'll give you a little preview. This is important when we talk about burns and severe burns and how skin can regenerate. as long as there's a little bit of hair follicles or sweat glands, something like that, some derivative of the surface, even if you destroy the skin can be recreated from these stem cells. If the damage goes down all the way through all the layers, the skin can never regrow, only the edges. But as long as you have a little bit, and you can see because these hair follicles go deep, you can have a regeneration of your skin pretty easily. All right, hair color. So much like skin color, as you produce genetically based, you produce pigments that go into the, in this case, the hair shaft, and comes out. And so eumelanin is going to cause you to have a lot of that. You're going to have black hair, most common in the world, black hair. And then browner hair means I make less eumelanin. And then pheomelanin, yeah, my goatee comes in red. Gonna have McKinney was my mom's maiden name, so I have some reddish pigment going off there. And of course, very red hair has just pheomelanin, depending how light or dark it is. So it's a mixture. You have genes that are going to code for eumelanin, giving you darkness, and then pheomelanin giving you kind of a reddish yellowish color. It's going to affect your skin and your hair pigment. And then, looking at the worldwide, I found this, I haven't, completely researched it, but black hair is going to be common in the world. Look at Africa, India, Asia, and it's dark hair is the common worldwide. And of course, the rarest hair is red hair, just a small percentage. And Scotland's #1, looking at percentage of redheads, and then you go to Ireland and Northern European countries. This is where it's this red hair evolved, and it's the rarest color. Very cool. And then various shades of blondes will be lack of pigment. And then as your hair gets older, it turns gray, you make less and less melanin. It's got less and less pigments on it. Polar bears actually have white hair. They're actually like fiber optics. Their skin is dark. You didn't know that about polar bears. They have dark, blackish skin, and then that's going to carry the sunlight in and help warm them up. But in case you didn't know what a red, black, and blonde hair look, I've illustrated that. Yes, and so pheomelanin really giving that reddish color to it. And of course, strawberry blonde, it's a continuum, definitely, but genetically based. But we have hair dyes too. You can have any color hair you want today, but natural hair color. And then curliness versus straightness is also genetically determined in the shape of the hair shaft and also the chemical makeup of it. Yep, and you'll have, as you get older, you make less melanin, and you become paler skins, and you will have gray hair. Just happens. All right, so interesting stuff. And there's no biological significance. I mean, the darker the hair, the more it's going to actually absorb more heat, in the tropics and absorb more UV radiation than lighter hair. Certainly it's linked. Looking at skin color getting lighter as you go farther north, and you see hair color. So the production of melanin is going to be linked to both skin and hair color. So they are linked. And you'll see things like red hair and freckles, and you say, boy, they go together a lot, don't they? But not always. You can be African-American and have freckles. So it's not always there. But the reason why is looking at freckles and red hair is that the genes they're linked, which means they're close together on the chromosome. So they're less likely to be separated when you do that crossing over. Oh, getting your genetics things going. So it's interesting that red hair and freckles are close on the chromosome, meaning that they tend to go together. They can be split apart, but they tend to go together because of just physical proximity. All right. Whew. So your hair gets oily, doesn't it? It's because of sebum, oil. And as I mentioned, it comes out with each hair to lubricate it, but also some other places. As you mentioned, the end of your eyelids too. You make this fatty substance, kind of keeps the tears from coming out. But yeah, on your skin in some places. Beautiful picture. This hair shaft has sebaceous glands everywhere. And so you can see they're light color, kind of frothy because they're lipids. And when you produce these slides, you use organic solvents and they wash away the lipids and they appear clear. So goblet cells appear clear, sebaceous glands appear clear, adipose tissue appears clear because it's just a matter of making the slides. You wash away the lipids, right? So this one you can see all these sebaceous glands making that hair shaft oily. Oh, look at this. Oh my God. I know you guys, you're like done with histology. We took the practical, you're done with your life, right? But look at the colors, look at the complexity, looking at your skin here. I mean, you got to appreciate, here's your epidermis, here's your dermis, here's your hypodermis, right? All right. And then you see all these hair shafts, beautiful hair follicles, right? And associated, see the SG, these are sebaceous glands, these kind of fatty glands that are going to have ducts that go right into the shaft of the hair. All right, sweat glands. Well, this is a way we can cool off. When we want to lose heat, there's various ways. Radiation is just losing heat to the environment. It's hard if you live in Arizona, it's 110 degrees out to do that. Conduction is if you sit on a cool tiles, maybe your dog kind of sits there, his old belly on the cool floor in summertime. It can conduct away some heat that way. Convection, we use air or water. Currents can take it away, right? And evaporation is a big one. If you put water and you go from liquid and you make it go gaseous form, it's going to take energy or heat with it. So we sweat. We sweat to lose heat. And two kinds of glands, eccrine or merocrine is your typical sweat glands. Lots of them on your forehead, your back. Where do you really sweat, right? And then Apocrine we'll talk about. These are special ones in our armpits and our leg pits that are stinky and that have their own use. So your typical sweat gland, it is a coiled, so it's not branched, but it's a long coil. It's found deep down there within your dermis or even lower. And it has a duct that snakes its way all the way to the surface where the product, the sweat, which is water, mostly water with salt and even some wastes, will be pushed out into the surface when it gets the appropriate signal. Your hypothalamus will have your temperature regulator in it. If you start working out, your muscles are really going to produce a lot of heat, your heart, and that heat is going to carry it in the blood. Your brain's going to say, dude, I'm getting hot. And it's going to send out a signal for your sweat glands to produce sweat. And that moisture will come up there. And also the blood vessels will be shunted to your skin to help radiate that heat, and evaporation of the sweat will take the heat away to cool you down. Yep, so a simple supercoiled gland is a sweat gland, and you have it throughout your body. Not everywhere exactly, but almost throughout your body, you have sweat glands opening to the surface. And because you get rid of, look at that, a little urea, a little ammonia, that old sweat is going to be broken down by bacteria to cause body odor. So it's part of the, skin can be part of the excretory system, gets rid of a little urea, you get a lot more, get rid of a lot more peeing it out. So if we're looking for it in histology, you're never going to find the gland and the duct perfectly because the duct twists and turns. And so you're never going to get a slice that catches it perfectly. But here you can see you catch little bits of it and you know what's going on. The sweat gland is carrying the product to the surface. Oh. And if you histology buffs really want to get into it, you can even look at a sweat gland and tell the difference between the glandular portion and the duct. They look different. Cool. All right, so that's your typical. You'll hear eccrine or merocrine, typical sweat gland. Now, apocrine are sweat glands that are found certain places of your body. They're bigger. And so if you look at them, the lumen, they're much bigger glands, and they're only functional from puberty on. So like I said, your kid smells pretty good. Suddenly teenage years, you need to get them deodorant, right? Because these apocrine glands under the influence of hormones become active. And instead of being this watery substance, they include a lot of protein material. And that's going to be stinky. And bacteria breaking down will make it stinky. So in your groin and your armpits, you have a lot of these apocrine glands that are functional at puberty. And they're really, they secrete a lot during sexual stimulation or fear. So under certain influences, you make a lot of product. And what comes out of these proteins, now these proteins are unique to you, right? Because proteins are made from your genes. And so there's going to be differences. So a secretion that is proteinaceous has the ability to send out signals about who you are and tell you how related you are. So animals, dogs would be sniffing butts and sniffing fire hydrants. They're getting a lot of information from a lot of apocrine glands in the anal region kind of thing. And they can tell about how closely related they are. They can also tell them if they're in heat and things like that. They have other information there too. But we probably give off signals in our sweat. And there's even been studies where you can smell t-shirts from strangers and relatives. And statistically significantly, you can pick out relatives' sweat. So it's very dulled, this sense. I think it's been pushed way back. But the ability to smell each other and get information about, you don't want to mate with close relatives, and you get information about the individual by the proteins given off, because those come from your genes. All right, just touching on this. It's a cool subject. But smell in humans generally is reduced compared to most mammals. Even your cat can smell better than you. Well, vision is taking the top priority for us. All right, so let's see. Here's an apocrine gland. You can see they don't open up. Unlike a sweat gland, they often open up again hairs in your down in your groin and in your armpits. And here's histologically, I don't know if you can tell, but the lumen is big. So they're just bigger glands. And there's fewer of them, and they're only concentrated in certain parts of your body. All right. All right, a couple more glands. Modified sweat glands. When you drink that glass of milk, put on your cereal, you are drinking modified sweat. Sweat that has a lot of fat, a lot of antibodies, a lot of proteins in it. So we have modified it to make milk in mammals. And I should throw also the ceruminous glands that make wax in our ear canals are modified to make very lipid-rich, waxy substance in our ears. But mammary glands, let's talk about them. They are breasts. They make milk in certain times under the influence of hormones. And we will see hormone prolactin, and then oxytocin helps push the milk out. So there's hormones that are involved in making milk. And then as mammals, we produce milk to feed the infants. And so milk production, the breasts really change late in pregnancy, and so that they're ready during when you're feeding the kid, the baby. And then once that's done, the milk production stops until maybe you have another kid. So mammary glands, modified sweat glands, they actually began evolution, we don't think to feed the infants. We think to provide antibodies to pass them between mother and baby. And we'll talk about that. But even in us, we have milk lines that go from our armpits through where our normal breasts are down to our groin. There's milk lines. And so you see a naked mole rat or pigs or squirrels or dogs or cats. You've seen your dog nurse the puppies. It has this long line of nipples and breasts, right? Well, we have two breasts in humans, but it's very common to have supernumerary or extra nipples. Breasts are pretty rare, but many of you out there have a mole that maybe you've noticed below your normal nipple, and it just seems like a mole. And some of it can even produce a little fluid. I mean, it just depends how it is, but I can look at the percentages, but percentage-wise, some of you I'm talking to have extra nipples that may just look like a mole to you, but if they're along that milk line, it gives you a clue that normally our genetics just express breasts in the breast area, two breasts. But normally the number of breasts equal about the normal litter size. Humans' litter size is 1. I know you're saying to yourself, I'm a twin. It's very rare. Triplets, incredibly rare, right? Beyond that's infinitesimally rare outside of our drugs that we take now to increase fertility. And even just sadly, when we were nomadic, when twins were born, sometimes they would smother the one twin because you can't carry two, you can carry one. And so, yeah, sad to say, but our normal litter size is one. We give a lot of energy into this one. In other animals, you'll see, look at your dog, normally the number of teats or nipples equal the litter size. Yeah. So these mammary glands are really modified to make milk, which is very rich in fats, and especially in seals and whales, it's just really fat rich, so they can grow quickly. Another thing is we're the only mammal that as adults drinks milk, right? It's weird, right? In another species, right? We steal cow's milk and drink it, so it's very strange. But a lot of the world doesn't eat milk, right? You don't see a lot of Asian cuisine using cheese or anything like that. And it's or African cuisine as well. But Northern Europeans developed a mutation to allow us to drink milk as adults, and we could steal it from our animals and allowed us to survive. And so we do. All right, so looking at the most primitive mammal, you guys know, platypus or echidna, they actually don't even have nipples. They have a milk patch where milk comes out and the babies lap it off the hair in this patch. Yeah, and so again, as you can read some papers on that, it's fascinating, the evolution of milk, and it's probably to extend to pass antibodies, not to give nutrition. And then we have nipples, that we have openings around the nipple where the milk is expressed and comes out. And then when you look at animals like goats and cows, they even have this kind of a cistern where the milk, if you know how to milk correctly, you let it gather and you pull it out. So they produce a lot of milk, and humans have enslaved all these animals to produce milk so we can have our cheese and our milk. All right, so mammary glands, interesting, huh? We have 2 in our breasts, and they only really develop in women under the influence of hormones. And we'll talk more about that when we get to reproductive system. All right, let's talk about specialized things like our claws. Like we have nails. Look at primates, we have flat nails. And your dog has claws, your cat. Same thing, just ours are flatter, theirs are more compact, but same exact thing. There are keratin that is very compact in like these sheets like this. Our hair is keratin and filaments. So very versatile keratin. Collagen and keratin are very versatile proteins in our body. So you look at nails, so of course we adorn them. We had some of you in class, great nails. My wife takes a lot of time. She likes her nails. And so I can appreciate nails. But they are simply derivatives of your skin. Just like instead of making the keratin on normal skin, we concentrate it to make this really thick nail material. And it protects. I mean, your little toe, that nail, that's on its way out. It's tiny, right? But, these are going to protect us when we claw, when we scratch, when we climb. And all that we do, they protect us, these nails. And interesting fun fact, your toenails grow exactly half as fast as your fingernails. You probably know that when you're clipping your nails, right? But on average, you can see, look at that, it's just on double the amount. Yeah. I have a lot of questions for this woman, how she lives her life with these nails, but I'm not going to ask them. So the anatomy of the nail, I want you to know this is called the lunula, like lunar, looks like a half moon. That's where the active cell division is taking place. You've got cell division going on, just like in your stratum basale of your skin. And then as the nail moves out, it becomes more opaque. You can see underneath it, the redness, the pinkness is your blood vessels underneath. That's why you can put an oxygen meter right in your finger, because you can see the blood vessels right there. And if your lips and your nails will turn blue too, if you have low oxygen. What else? The cuticle, this is this area here, the skin, you often have to push back. So you don't have to know this. I'm not going to ask you this term, but underneath it will be this nail bed, and this nail plate will be on top of it, and the nail grows out from the cuticle outward, right, as it grows longer and longer. Histologically, you can see here's the nail that we see, here's the cuticle covering it, and then the nail that comes out, the part that's hidden, and it's on this nail bed. Cool. Here are these Piscinian or We learned them as lamellated corpuscles. You can see a lot of touch receptors there too. Oh, I thought I had to put a slide on tattoos. We're talking about skin. It's so common. And again, so common. They weren't when I grew up. You know, tattoos were sailors and prisoners and tattoo people. I don't know. And now I'm rare not having a tattoo. When you see someone that has no tattoo, it seems to be the rarity. So they definitely come back big time, the tattoos. And what is this? This is what a tattoo is. If you were to put pigment into your epidermis, it would be gone. Just like your tan lasts about 28, 30, 35 days. As the melanin comes out and your skin cells die, they take the pigment with it. But if you put pigment in the dermis, it's going to be permanent because the dermis is permanent structure. The epidermis is always coming up, right? So that's the deal. You just put pigment into your dermis and it's pretty permanent. It'll change, you know, tattoos will fade, sun will still be able to get to them, and your body will react to it somewhat. If you want to get rid of it, they use lasers to break it apart, and then your white blood cells will eat up the pieces. But yeah, you put pigment into your dermis and it will stay there usually pretty well. And skin repair. You all know one of the beautiful things about us. We'll talk about clotting, how you get a leak in an artery, it freaking fixes itself. It's amazing, you know, and your skin, you know, you get a cut, it may look horrible. You get a huge, I've had so many cuts and abrasions, and I think about it now, it's like, wow, my skin really repaired itself. In many cases you can see scars, other cases you can't. So this ability to repair your skin amazes me. It's really, really cool. And all you need to repair it, again, is some vestiges of that epidermis. They can be, even if you scrape the hell out of your skin, you remove it all, as long as it's not too deep, you've got some hair follicles, right? Way down in the hypodermis. You got some sweat glands down there. You need some of that. Those cells under growth factors will wake up and start dividing. And you can regrow that skin. If you get a third degree, we're talking about all the layers of the skin, then it can only grow from the edges. And so then you're talking about skin grafts, things like that. But you look at this, you've got a cuts, and here, this is a scab. You'll have this dried blood serum, and blood will be up there in the scab, and it will grow. It'll kind of protect it as the epidermis grows underneath it. And we see here, see that stars where they're coming together. And once that epidermis comes together, that scab can pop off, and you got kind of fresh-looking skin, but it will grow into itself and become normal again. So you will see in any kind of damage to the skin, you will see a redness, a swelling, pain, will become warm. It's called the inflammatory response. Inflammatory response, again, histamine and heparin are released, causing more blood flow, swollen, white blood cells will start cleaning up the debris, fighting any kind of bacteria. And you'll have blood will clot in there, right? And it's going to form this scab. And then below the scab, you're going to have phagocytes cleaning up the debris, fibroblasts making collagen fibers to try to strengthen it beneath. So all these things happen. We'll talk about bone repair. This is skin repair. So it shows you have this huge divot, this kind of injury, right? Blood. Blood's the first step. Your blood is going to bleed into it. And then you'll see that underneath it, you're going to have, you can see skin is going to start regrowing. Lots of white blood cells cleaning up the mess. And depending how well this cut is, if it's too big, you're gonna have a lot of scar tissue will form, a lot of collagen fibers. But if not, if you can, that's why sutures help. You know, if you get a big cut, if you sutures will bring it together to lessen that scar. But in either case, it's gonna heal. Just depends what it's gonna look like. And burns, just so you know the basic terminology, a first degree burn, serious, you get a sunburn, is going to turn red, heat, painful. A few days later, skin cells will start dying, it'll peel, that's cool. Second degree is going to be called partial thickness. And still with this, you have the ability to repair. And these burns can be caused by chemical burns or hot metal, or it can be radiation, various kinds of burns that are going to really affect it. And then third degree burn is when you are in some serious problems in terms of healing. And so what are they going to do about it? You're going to be put in a certain room. You're going to have debridement. They're going to have to keep it clean. And it's, oh my God, without your skin, the possibility of infection is huge. And your temperature is going to fluctuate. So you know how important skin is when you lose it. But you can have a skin graft. And an autograft is come from your own skin. And so if you have a problem here, you can take some skin from your butt or somewhere you don't notice it as much and graft it on there. It will grow. An allograft is other, like an allele, other, and it's a temporary fix. Cadaver skin, they're making artificial skins, but it's going to cover it, let it repair. But an autograft is your own skin. Your body's not going to reject that. All right, body temperature, just to talk about that quickly, realize that you've got to keep a steady body temperature. And if you're too cold, your body can ramp up metabolism. It can shunt the blood from your skin to your core. So you turn kind of ashy, but it's protecting the heat. And worst case, you can shiver. You can use your muscles and try to release some heat. If you're too hot, that's also, either case is deadly. You know, a high fever above 104, you're in big trouble. Then your body's going to go into a mode where it's going to shunt blood to your skin, and sweating will help reduce that heat. So that's what your body's got, shunting blood between your skin or not, and it's got the sweating and shivering too. Yeah. So indeed, your body, especially you work out, you get hot, you start sweating, right? So your skeletal muscles give off a lot of heat if you're really working them. I mentioned these earlier, but here it can illustrate how heat can be transferred through radiation, through conduction, convection, and evaporation of sweat. Yep. And again, this just shows you, I'm not going to go through it all, but if your body's too hot, your hypothalamus is made aware of that, and then your brain is going to say, dude, let's start sweating. Let's shunt blood to my extremities, my skin. So you get in a hot tub, you turn red, and your body's trying to shunt that heat. And the opposite end, I think I've described it well enough. If you're too cold, your body shunts it away into your core, your blood. Stop the sweating, obviously, and maybe even shiver if you need to. And so the terms you're all familiar with, of course, is hyperthermia, is getting too hot. And this is a serious thing. I was taking my temperature the other week. I got to 101. You know, it's not too worried about it. But if it gets up, if you have a kid and they have a fever, actually, that's good. I mean, when you take Tylenol, things, antipyretics will bring your fever down. But you don't want to do that necessarily unless it's getting dangerous, because your body purposely sets the temperature higher because it's bad for the microbes and it's better for your immune system. So it used to be thought you always fight a fever, you know, but now there's a lot of thought is that you let the fever. It's not, it is your body's doing it on purpose. So realize that. But once you get up, if you're at 100, 300, 400, 500, that is dangerous, you know, especially bring the kid right to the hospital if they're 104. Because the danger is with high heat is that you're going to denature your proteins. You're going to screw up your enzymes and it's irreversibly death. Okay. So high temperature, critically important, critical to life, right? And then hypothermia is too cold. And really there's less of an issue. Certainly when you get too cold, your organs start failing and et cetera. But you can come back from, you have kids that are trapped under ice that their body temperature is just ridiculously cold and they can bring them back. Too hot is going to denature your proteins. You don't come back from, you know, frying an egg, you know. An egg gets too cold, you can bring it back, basically, when you look at proteins. But in either case, you know, kind of the symptoms of hypothermia, you're going to feel hot, obviously. But there's a point where you might even stop sweating and you're having a mental confusion. That's dangerous. You need fluids. You need to cool your body down. Hypothermia, also, you feel cold at first, but then you're going to begin, if you start having headaches and start feeling disoriented, that's kind of some of the dangers of hypothermia. And realize we actually put people purposely in hypothermic state when we do a heart transplant, other things. So we can either put ice packs on you or actually take your blood and cool it and give it back to you. We can bring your body temperature down when we want your metabolism to slow. When we're worried about your brain not getting enough oxygen, we can slow everything down for surgical needs. All right. And lastly, well, we'll talk a little bit about melanoma and skin cancer, but of all the organs, when we talk about aging that you can see and notice in a person, how can you tell their age? The skin and the hair give it away. Wrinkles, they happen, they're real. What's going on in age is that your skin thins. You have less collagen, less elastin production, less fat in the subcutaneous region. All these things lead to your skin wrinkling, right? Baby's got all this fat, it's all stretched. And people put fat injections to get rid of wrinkles if you want to stretch your skin out. So that happens, your sweat glands and sebaceous glands, less activity. And so you're going to get age spots are going to form. You're not going to be able to, your temperature is really hard to regulate as an old person. So they've always got the heat up. They always got their sweaters because you have less ability to regulate temperature as you get elderly. Yep. Hair thins. Along with your skin thinning, it heals very slowly compared to a young person. Yeah. And so they have vitamin D problems issues too. As you get older, you spend less time in the sun. And so they show calcium deficiencies too. So all these changes in the skin as you get older, the thinning, the less elasticity, the loss of body temperature control, you'll see graying of the hair. All these things need to be, watched and taken care of in grandma. All right, I can't talk about skin without quickly talking about skin cancer. Definitely, these are all kinds of moles. And I just taught pathophysiology. I went through, as a nurse and such, talking about all the different types of skin bumps and nodules. There's names for all of them, right? A rash, is it small? Is it pustulate? Just describing the types of pus. It's amazing. Yeah, so purulent, very pussy or watery. So yeah, I got into that teaching pathophysiology. I learned quite a bit actually. But moles are a problem. Yeah, me being fair-skinned, my grandpa died on my mom's side of a melanoma. Started and the leg I was told is just a mole. So these are things, especially fair-skinned people that have burned their skin in their lifetime, they're more at risk. So it's the most common cancer is skin cancer, but it's not the most common killer. I mean, lung cancer, pancreatic cancer are deadly cancers. Skin cancer, in many cases, it's just removed as an outpatient, burned off or cut out very easily. So it can happen in any of these skin cells. Basal cell or squamous cell, these are both cells in the keratin layer of your skin. They're often lower lip, lobstermen, lower lip and ears. Years of sun exposure will cause these skin issues. Nose, right? So the most common is going to be the squamous cell cancer, and it's also the least deadly. Adenocarcinoma happens in the glands. I don't have time to talk all about cancer, but the other kind of cell we worry about are the melanocytes. And it turns out melanoma, cancer, these melanocytes, is much more dangerous. It will form, that kind of a melanoma is usually more colored, different colors, and it can spread outward. Cancer means crab. It's like the legs of a crab, look like into the tissues. But if it goes deeper, then it can really spread, and melanoma can turn into lung cancer. Can be very deadly. So looking at your skin issues, and all kinds of little things on me, I'm light skinned, but you can see you want to follow, and then the A, B, C, D, E even. Again, asymmetry, is it not symmetrical? Does it have a ragged border? Is the colors, are different colors in there? Is it big? And the E is evolution, is it changing? And so many people, it's hard to tell, is that mole bigger? I don't know. People will take a picture with cell phones now of their back, maybe a quarter of a scale. And that way take it every year and you can say, oh, this thing is actually growing or not. So if you're really good, you'll take pictures of your skin every year. And so you can tell your dermatologist, is it actually growing or not? You have evidence. And so, if you have any of these skin cancers, they will do a biopsy and to see, try to get all the edges to see if they've removed it completely. And the fear is the skin cancer spreads. If it's in your skin, you can remove a piece of your skin. but you want to watch those. All right, some important points. There we go. I have given you 2 lectures on skin, 1 big lecture, split in half. As organs go, it's important. It is our face that we present, and talked about some of the functions of your skin that go beyond just your appearance, of course. So, all right, I think we are good. Skin lecture. Any questions, you guys, just let me know.